Okay, so today we're talking about inverse functions. We've done a lot of work on these before, but in this case we're looking at specifically inverse functions of exponentials and logarithmic functions. They are quite special because if we have log of base a, the inverse function is the exponential of base a. And we'll do a few examples to prove that is the case. Can you take a minute and pause this video and think about what we know about inverse functions? We've covered them before in earlier chapters, so just take a minute to write down what do we know about two functions that are inverses. Okay, so if you've done that, let's see how many of these things you've got. So we know that our inverse function is reflected across the line y equals x. We also know that the asymptotes swap. So if we have a horizontal asymptote, as we do with an exponential function, the inverse, the logarithmic function, will have a vertical asymptote. We know that the xy coordinates swap. So if we have a coordinate point xy, in the inverse, it would become the point yx. We also know that the domain and range swap. So the domain of the original f is equal to the range of the inverse, and similarly the range of the original is equal to the domain of the inverse. Other things we know that if there is a point of intersection, at least one of those points of intersection occurs on the line y equals x. We also know that to work it out we need to interchange x and y. And I think that's probably the main things. We also know that for an inverse to exist, the original must be 1 to 1. So there's quite a few things we've covered before when we've talked about inverses, and all of these also apply to our exponential and logarithmic graphs. So let's have a look at this specific example. We've got our original function log base e of 3 minus 4x. The domain of the original function is just given as d. We can work out what that is for our new function because we know that the argument in here must be greater than 0. So the domain we can work out by having 3 minus 4x greater than 0. That means negative 4x must be greater than negative 3, subtracting negative 3 from each side. If I divide by negative 4, dividing by negative, the inequality sign will swap direction. So I'll get that x has to be less than 3. That means that our original domain given here is actually equal to less than 3 on 4, so we start at negative infinity and go to 3 over 4. So that's our domain. Now we're wanting to find the function f negative 1. So to find our inverse function, we have to interchange x and y. Same as we've done every other time we want to find inverse functions. So that would give us the equation x equals log e of 3 minus 4x. Oh, sorry, interchange x and y, that should be a y. So we now need to swap these over. We need to try to solve for y. First step, most logical step, will be to get rid of this log base e. We want to try to focus on trying to get 3 minus 4e. We're looking for the y. We're wanting to get y on its own. To move the log base e, we can change this to an exponential equation. We had base e here, so we will have base e here. The x becomes the power, and we get it equal to 3 minus 4y. I can subtract 3. Ex minus 3 equals negative 4y, and then I could divide by negative 4. That would give me negative a quarter, e to the power of x, dividing by negative 4. If I divide negative 3 by negative 4, I will get plus 3 over 4. This is almost the answer, but not quite, because I want to find the function f negative 1. When I'm finding a whole function, that means I need to determine the domain as well. The original function had a domain of negative infinity to 3 over 4. Because it was a logarithmic function, and because we had a negative 4x, that means it would have had a shape like so. It had a negative 4x, the x values had been swapped, it had been reflected across the y-axis. So what that means is that the range of the original function would be the reals. So here, the domain of the inverse would be the reals. So our function f negative 1, domain is r, to codomain r, we never change that, of f of negative 1x equals negative 1/4 e to the power of x plus 3/4. Okay, moving along, we can now look at sketching this graph. So we're sketching the graph of f and f inverse on the same axes. We've got to be really careful here. So if we are looking at sketching this, let's think about where things are. Let's think about if we're going to get any x and y intercepts. Our asymptote here is at 3/4 for our log graph, because we know that x has to be less than 3/4. So let's get a bit of a scale going, okay? So if we're thinking about a scale, 1, 2, 1, 2, half would be halfway in between each of those. So 3/4 is going to be here, like so. Please be careful with your scale. While you don't need to use a ruler and make sure it's 100% accurate, it does need to be reasonable. And we label the asymptote with the equation x equals 3/4. This is our shape as we decided before. Because it's a negative 4x, that means it's being reflected across the y-axis. So we have a shape like so. A shape like this, if I was drawing it, it's going to cross both the x and the y-axis. So I need to find the x and the y-intercept. If I'm finding the x-intercept, that means I need to substitute in y equals 0. So I would get 0 equals log base e of 3 minus 4x. We're wanting to solve from x. So again, we need to apply all the rules we learned about exponential equations and solving log equations to solve this. To get the x on its own, I need to move the logarithm, which means I need to convert this to an exponential equation. E is my base, so e is still my base. The part on its own becomes the power. The argument, the thing within the log sign, is what we get there. E to the power of 0 equals 1. We can continue, we can subtract 3 from each side, negative 2 equals negative 4x, and now I can divide by negative 4, which would give me a half. So we know x has a value of a half. Well, that makes sense, it would be this point here. So far, so good. If we work out the y-intercept of the original, that means we substitute in x equals 0. So I would get y equals, I'm substituting into my f equation, so I'm doing this for f of x right now. Y would equal log e of 3 minus 4 times 0 is 0, so y equals log e of 3. Thinking about what we know about values, about where this will lie, well, we know log e of e is 1, and we know that e is 2.7. We know that log e of 1 is 0. This is going to be bigger again, okay? We've gone from 1 to 2.7 and our log value has gone from 0 to 1. We need to increase again to find log e of 3. It's not much more than 2.7, so it's probably going to be not much more than 1. So we get our value here. We sketch, make very certain that you've got one smooth curve. Make certain that it's starting to, it's not asymptotic, but it's relatively flat, our log graphs. Make it clear that it approaches the asymptote here. Label, we always label key features with coordinates. So this here is the point half 0, and this here is the point 0 and log base e of 3. We label our curve as well. This is my f curve, the original function. We We now need to sketch the inverse. So to sketch the inverse on the same axis as it says, we swap everything around. We did have a vertical asymptote at x equals 3 on 4. So for our inverse, we will have a horizontal asymptote at y equals 3 on 4. And that makes sense as well. Looking at our exponential equation, it's been translated up 3 on 4. So 3 over 4 will be here. And we get the equation y equals 3/4. Our x and y intercepts swap as well. Our original x-intercept was at half 0, so our new y-intercept will be at 0, half. We had a y value here at 0 log e3, so our new value will be at log e3, 0. Remember, we established that log e of 3 is a bit more than 1, so it will be over here. Our shape, it's a negative exponential, negative the whole thing. It's been reflected across the x-axis because the y values have changed. So it's going to have a shape like so. It approaches our asymptote, it cuts through those 2 points, and it continues to increase exponentially, so it's increasing more and more as we go. We label our points. This is the point 0, half. This here is the point log e3, 0. We label this curve as f to the power of -1. Please be careful when you draw these. Some people start by putting their 2 asymptotes on and then draw this curve almost like a hyperbola so that it doesn't cross either the blue or the green asymptote. You need to be careful. When drawing the exponential graph, it only has a horizontal asymptote. This blue line here, this blue asymptote, is not relevant when I'm drawing my exponential graph, when I'm drawing my green graph. Because exponential graphs only have horizontal asymptotes, they don't have vertical asymptotes. Notice that they do intersect just here, and it does look more or less like that point of intersection is on the line y equals x. We generally will not ask you to find points of intersection in a tech-free situation because it is quite difficult to do. It's not straightforward. If you need to find the point of intersection, do so using your CAS calculator. So that's how we sketch. Same as always, we make sure our graphs are clear, easy to read, have a reasonable scale, have our coordinates given, all key points given as coordinates, and if we've got 2 graphs, we've labelled them. Okay, the next question we want to look at for inverses. We're now looking at a past exam question. This was from a while ago in 2006, but it is still relevant today. So we're looking at where we've got a function f of x equals log base e of x to the power of 4. Now it's a really good idea when you get functions, particularly functions you might not be familiar with, to draw a quick sketch on your CAS calculator. So if we have a look on a CAS calculator, let's go to our graph menu. Now I have done this earlier. We've got the equation ln means log of base e, and you can find ln just here. So I've typed ln log base e of x to the power of 4. ln means log base e. So we've sketched it. We can sketch the graph, and I will zoom in as well, and we can see this is what it's looking like. Now this does make sense as well. It's the function log base e of x to the power of 4. Now normally log base e of x, we would just have this one branch here. Because it's x to the power of 4, this function is also relevant, it's also defined for negative values of x. Because if I was to substitute in a value of -2 to the power of 4 becomes positive 16. So any value I substitute in here, -1 is equal to -1 to the power of 4 is equal to positive 1. So what we're getting here are values that are defined for every value. Except, of course, where x is 0, because we cannot have log of 0. We can't have log of a negative either, but in this case, we never are going to have log of a negative. So considering the options, and again, I recommend that you pause the video, take a moment to think about which answer will be correct for yourself. Once you've had to think about it, we need to consider our options. We're wanting to know for this to have an inverse. Inverses must be one-to-one, so we have to restrict this function to make it one-to-one. We consider our options. Our domain goes from a to infinity. If a has a value less than 0, that's like saying a has a value of -2, for example. Well, if I had a domain from -2 to infinity, it would go down and it would come back up here. That is not one-to-one because a horizontal line test, it crosses twice. So therefore, a is not correct. That will not give us an inverse. If I had a value of a less than or equal to -1, that means my endpoint could be less than or equal to -1. It could be -1, it could be -2, it could be -3, it could be many other values. Sorry everyone, my computer's decided to go to screensaver mode. Okay, there we go. Alright. No matter which of those values we took, if we then went from these points to infinity, it's not going to be one-to-one, going to cross twice. A less than or equal to 1, so that means I could have values of 1. Well, from 1 to infinity, that would be fine. But it's also saying I could have values of I could have values of -1 or of -3. They're all less than 1. If I took those values of a to infinity, it's not going to be one-to-one. A greater than 0, so in that case, we're taking values greater than 0. So that could be where x was 0.1, or x is 1, or x is 3. Those are all values where a is greater than 0. For any of these points, if I then continue to infinity, my function is one-to-one. If we draw a horizontal line, it will only cross through once. So D is our correct answer. We can consider E as well to make certain that we were correct. Well, A greater than or equal to -1, if I took an option of A equal to -1 and drew from here to infinity, no, it is not going to be one-to-one. So our final answer there is D. That's all we're going to do for inverses right now. We will look at this a little more in class, but for now I want you to remember the process is the same as we did for inverses earlier this year. Solving to find the x and y intercepts is just using all of the skills we've learnt about how to solve exponential and log equations that we've learnt earlier on in this topic. So that's all for exponentials and logs inverses.